You ever plug in one of those Ethernet cables and just stop and think? Like, what is actually going on in there? How does me clicking on something here turn into something that a computer, maybe thousands of miles away, can understand? Well, in this explainer, that's exactly what we're going to do. We're going to pull back the curtain on that whole process, starting right from the very beginning, that first little pulse of electricity.
And this quote, it really nails it. When we talk to each other, it's not just random sounds, right? We have rules, things like grammar, we take turns speaking, we know when it's time to listen. Well, it turns out computers are pretty much the same. They absolutely need a shared rule book, what we call a protocol, to make sense of everything. Without it, it's all just a jumble of electrical noise instead of a real conversation. All right, so here's the plan for our journey today. First up, we're going to look at that rule book for communication. Then we'll get down to the nitty-gritty, the actual physical cables and signals. After that, we'll explore how networks got a whole lot smarter, how all our data gets wrapped up for delivery, and finally, how we take that local chat and connect it to the entire world. So, to keep all of these rules from becoming a total mess, the experts came up with something really clever, a model. You can think of it like a blueprint. It takes this huge, complicated job of networking and breaks it down into smaller, much more manageable layers. The beauty of it is that each layer has one very specific job to do, and they all just stack on top of each other to make the magic happen. Okay, and this is the 5-layer model we're going to be working with. The best way to get your head around it is to think of a delivery service. Seriously. Down at the very bottom, you've got the physical layer. That's the actual road the truck drives on. Then layer 2, the data link layer. That's like all the local street signs that help you get around one single neighborhood. Layer 3, the network layer, that's the big highway system that connects all the different cities. The layers on top of that deal with sorting the mail and what's actually in the package. But for today, we're going to keep it simple. We're focusing on the absolute foundation, how we build the roads and navigate that local neighborhood. All right, let's dive in. We're starting at the very bottom, layer 1. This is where things get real, you know? It's all about the tangible stuff you can actually hold. The cables, the connectors, and the physical signals that are responsible for carrying all our ones and zeros from point A to point B. So, at its most basic level, the job here is to take those abstract digital ones and zeros and turn them into a real physical signal. The way you see this most often is with good old copper cables. You can basically think of a high voltage as a 1 and a low voltage as a 0. Simple, right? The other major player is fiber optics, which, well, it's just super cool. It uses tiny pulses of light. Now, fiber is ridiculously fast, and it doesn't care about electrical interference, but, there's always a but, it's also a lot more expensive and a bit on the fragile side. And the special technique that makes all of this work, it's called modulation. That's really just the fancy formal name for the process of changing a signal to represent data. And yeah, it might sound pretty simple, but believe me, perfecting this process, that's the secret sauce that lets us shove billions of bits through a simple copper wire every single second. It's pretty amazing. Okay, let's take a little trip back in time. In the early days of networking, the simplest way you could connect a bunch of computers together was with this device called a hub. Now, a hub is a true layer 1 device. What does that mean? It means it's dumb. It only understands one thing, electrical signals. It has no idea about data or addresses or where anything is supposed to go. So when a signal comes in on one of its ports, its only job is to amplify it and just blast it out to every single other port. As you can imagine, this blasting everything everywhere behavior created a massive problem. It's called a collision domain. The best way to picture it is a really chaotic party where absolutely everyone is shouting at the exact same time. Total chaos, right? Nobody can understand anybody, and that's exactly what happens on a network with a hub. If two computers try to send data at the same time, their electrical signals literally crash into each other on the wire. The data gets all scrambled, and they both have to back off, wait a random amount of time, and then try again. It is, to put it mildly, incredibly inefficient. So, how do we fix this shouting party problem? Well, for that, we need to move up the stack to layer 2. This is where networking starts to get, well, a whole lot more intelligent. And this really shows the huge leap forward we made. We went from the hub, which is basically a dumb broadcaster, to the switch, a smart director. So instead of shouting every single message to every single person in the room, a switch actually learns which device is plugged into which of its ports. And then it sends data only to the device it's supposed to go to. This intelligence, right here, is the reason a switch solves that collision problem, and frankly, why it costs more than a hub. This one change was an absolute game changer for network speed and efficiency.
But this brings up a really important question, right? If a switch is going to be the smart director, it has to have some way to uniquely identify every single device that's plugged into it. It needs some kind of addressing system. And the answer to that question is the MAC address. Honestly, the best way to think about a MAC address is like a physical fingerprint for a network device. It's a totally unique serial number that gets permanently burned into the hardware by the manufacturer. Every single network card in the entire world has one, and no two are ever the same. So just how unique are we talking? Well, a MAC address is a 48-bit number. That gives us, get this, over 281 trillion possible addresses. That number is so astronomically huge, it pretty much guarantees that every network device ever made, or that ever will be made, can have its very own distinct identifier. A little fun fact, the first half of the address actually identifies the manufacturer, and the second half is the unique number they assign to that specific device. Okay, so we've got unique addresses, and we've got a smart device, the switch, that knows how to read them. So what's next? Well, now we need to look at how the data itself is actually packaged up for the journey. And for local delivery, this digital envelope is called an Ethernet frame. The easiest way to think about building an Ethernet frame is to picture yourself preparing a package for shipping. First, you have something called the preamble, which is basically a little heads up that says, hey, get ready, data's on its way. Then come the two most important parts for our switch, the to and from MAC addresses. After that, you slap on a little label that describes what's inside, and then, of course, you put the actual data in the box. And finally, you seal it all up with a special code, the frame check sequence, which is there to make absolutely sure nothing got damaged along the way. And that final error checking part, it's actually really fascinating. It uses this clever piece of math called a cyclical redundancy check, or CRC for short. Here's how it works. The computer sending the data runs a calculation on everything inside the frame and tacks the answer onto the end. The computer on the other side receives the frame and does the exact same calculation. If the answers match, perfect, the data's good to go. But if they don't match, it means something got corrupted and the entire package just gets thrown in the trash. So switches and MAC addresses, they are absolutely fantastic for talking inside a single local network, like in your house or in an office. But what happens when you need to send some data to a server that's on the other side of the planet? Well, for that, we need to climb up one more layer in our model. And this is a really key distinction to understand. A switch is like the local mail carrier. It manages all the traffic inside one neighborhood, the LAN. A router, on the other hand, is like the entire national highway system that connects all the different neighborhoods together. Routers are layer 3 devices, and they don't really care about MAC addresses. Instead, they use a whole different addressing system you've probably heard of, IP addresses, to move data between completely separate networks. And when you connect a bunch of networks together like that, you get a network of networks, an internetwork. And the most famous internetwork of all is, you guessed it, the internet. Okay, let's bring this all together and look at the big picture. We've gone through a lot, so why does any of this actually matter? Why is knowing this stuff so powerful? I mean, just think about the journey we just took in a few minutes. We started with a simple pulse of electricity on a wire. That became a stream of ones and zeros. That stream got packaged up into this perfectly structured envelope with addresses and error checking, and then it got delivered by an intelligent switch. You see, understanding these fundamental layers, that is the key to figuring out almost any network problem. Because now you know how the whole system is supposed to work, right from the ground up. It really just goes to show you how these simple technologies we rely on every single day are built on these incredible hidden layers of complexity. It's a pretty great question to think about, not just for networking, but for all kinds of things in our lives. Hey, thanks for joining me on this deep dive, and as always, keep asking questions.